Hi, my name is Junwei, and thanks for watching this video. The title of this presentation is Locating Microseismicity from Surface Monitoring Arrays Using Symmetry-based Grid Search and Hypocenter Inversion. It's a case study. So basically, in this talk, I just want to introduce you a workflow that is characterized by symmetry measurement and hypocenter inversion. The idea is similar to what we've seen in this video for Amazon. We would like to have a processing unit, something like that. When microseismic data flows from the monitoring site, we would like to have a processing unit like this that is continuously checking the data and giving us feedback. The resolution can be high at the post-processing, or the resolution can be low for the pseudo real-time feedback purpose. So in the following, I'll give you the details of the four-step workflow. The first step is to calculate the travel time based on your isotropic or anisotropic reservoir model, and then use the symmetry-based grid search to locate events. And once we located the events, we can plot up the predicted arrival with the waveform and use the cross-correlation method to refine the arrival, and the differences between the predicted arrival and the refined arrival is used to invert the hypocenter or relocate the events in a manner similar to Geiger's method. We apply this workflow to 24 hours of recording of surface seismic data. After a major earthquake that we thought it may be related with oil and gas activities, a few seismometers were deployed just to capture the seismic activities in those regions. And using a moderate processing parameters, not very high resolution, not very low, we managed to locate more earthquakes that are not recorded by the global seismic graphics. And that gives us a better idea of the local seismic activities. And then I'll draw some conclusions and discuss some possible applications. So let's start the workflow. Step number one, calculate the travel time table for both P and shear wave direct arrivals, because the grid search would need the travel time between each pair of the source or the grid within the search volume and the receiver. And in our case, we use a faster sweeping method to calculate the travel time. It's simply a finite difference method of solving the econo equation for the travel time field. Unlike two-point ray tracing, that each calculation just gives you the travel time of each pair, the output of the faster sweeping method is the travel time field. So each calculation for one source can give you the travel time for all the receivers. Usually, the grid outnumber the receivers. We're talking about probably 10,000, 100,000 grid points, but we only have 10 or 100 receivers. So for computation efficiency, we treat the receivers as the virtual source and calculate the travel time at all the source location. Here is example from isotropic heterogeneous velocity model. The velocity is very complicated, but using a single core, it takes about less than 5 seconds to calculate the travel time of P wave on 10,000 grid points. The P wave travel time field is plotted in isosurface, so you can see the wave is probably getting away from the point source. The other example is from homogeneous orthorhombic velocity. The wavefront of the fast shear wave is not spherical anymore because of the anisotropy. It takes about 30 seconds to calculate the travel time for 100,000 grid points, so it's quite efficiency. The details of this method has been published last year in the EAGE conference. So now we have the travel time table, we can launch the grid search, and using the symmetry measurement as the image condition to get a time independent 3D function. So the details of the symmetry measurement is outlined in our SEG conference paper last year. And we can also add extra flavors like semblance enhancement to improve the signal to noise ratio. We can also add a polarization enhancement to reduce the spatial ambiguity, and I'll get to the details later. The signals are usually too large to fit in the computer memory, so we have to design a signal window to take a bite out of the data. The size of the signal window is decided by the size of the scan window, the travel time table, and the size of the grid search box, search volume. So The, the, the signal window has to be large enough to include the slowest possible arrivals from the search volume. So you can imagine the larger the search volume, the longer the signal window. The scan window, the size of the scan window is decided by the user. And the scan window is just to scan, as you can see here, through the signal window for the waveform in the signal window for all trial origin time. And these two windows go through the data files and append the new data files to the end of the other in order to avoid the missing events recorded by two files. And we repeat this procedure for every single grid within the search volume. And this procedure is actually a stacking procedure. And we get a function of space and origin time. Here we just use semblance as an example, but it can be any other seismic attribute like the true amplitude, like the short time, long time, analysis window ratio. Instead of summarize the amplitude, the amplitude within an arbitrary window, we use the symmetry measurement. So what do I mean by symmetry measurement? It's an image condition adapted from time reverse acoustics. If we re-inject the recorded seismic signal on the surface back into the model, and we're monitoring the amplitude at the true source location right there, we will see the amplitude there actually is symmetric about its true origin time. And that symmetry is degrading as you move away from the true source location. The same applies to the semblance, for example, or any other seismic attributes you used in your stacking processing. At the true source location, the travel timetable best follow the waveform, but only reaches the maximum when the trial origin time equals to the true origin time, as you can see here, and tails off before and after. So we use the signal before the maximum value and cross-correlate the signal with the signal after the maximum value, and use the cross-correlation value to quantify the symmetry. So at the location that is not the true source location, you hardly see any symmetry, so the measurement is low. This is just the equation describe what I just said, and this is how we get a function that is independent of the origin time. And then the grid points that maximize this function is considered as the grid point, the location of possible events. So we repeat this for all signal window, and we can plot up the maximum f function value with time. It's easy to see when there is a true events, the function value will stand up and saying hello. If there's no true events, it will stay very low. However, this is from a numerical experiment. As you can see, the true signal is plotted in the blue line. You can see a P wave arrival and a shear wave arrival. After we add a high level noise, the signal looks like the black line, and you hardly observe any arrivals. But the noise there is incoherent, so the stacking significantly improved the signal to noise ratio. In a reality situation, the f function value varies a lot, and here is the example. The vertical axis is plotted in a logarithm scale, and every single red dot corresponding to a possible event, and most of them are false alarms because the coherent noise in the real data sets. So a trade-off threshold value has to be decided because we don't want to exclude too many true events, but we also don't want to include too many false alarms that will increase our workload in the post-processing. So if we have set a high threshold value, we only process large events. So of course we have less false alarms, but we only focus on the strong events. And that's the meaning of low resolution. And if we have a very low threshold value, and of course we'll include a lot of false alarms, but of course a lot of weak events, as weak as the coherent noise. And for the polarization enhancement, we all know the P wave is polarized along the ray path, and the shear wave is polarized on the plane perpendicular to the ray path. So in a single borehole layered model case, if the true source location is here, the grid points along this curve can match the travel time equally well. Without the polarization, we don't know where is the true source location. So if we include the polarization, we can reduce the ambiguity to an area that is more close to the true source location. But our experience shows that We only apply the polarization analysis constraint when we have good velocity model. Otherwise, the constraint from the model is too off from the reality, and they actually introduce the bias into the location. And by saying good velocity model, we mean a velocity model well calibrated. It captures the heterogeneity, lateral heterogeneity, as well as the anisotropy in the reservoir. So let's say our processing unit tells us their events located, so we can plot up the predicted arrival with the waveform. So the blue line is the predicted arrival, and the waveform is in a black and dark density. And this looks like a false alarm because it doesn't match the waveform at all. It only matches a very small part, and that's why it was triggered as events. So we can disregard this event and move on to the next one. The next one looks more reasonable. The predicted arrival more or less follows the waveform, but if we flatten the waveform following the predicted arrival, you can see the mismatch, because that's the error in the location and the error in the model. So we have to use a cross-correlation method to refine the first arrival, and it's done in a semi-automatic way. The details is in this paper, and according to the author, this method can save up to 80% of the processor's time independent of the number of traces. Here I think we have like more than 1,000 traces. It's just take a few mouse clicks to refine the events. So if I flick back and forth, you can see the effect of the cross correlation. And just want to mention the cross correlation is not the matched filter that people used in signal processing. So now we have the differences between the predicted arrival and the refined arrival. The differences is used in the fourth step, the nonlinear inversion. And we have two small loops. Loop A is to invert for the origin time, and loop B is to invert for the location. And we repeat these two loops iteratively till the differences between the predicted arrival and the observed arrival is minimized. And actually, this is from a workshop from a workflow of passive tomography presented last year in a conference in Iraq, and actually this conference a few days ago. If we have adequate ray coverage, like in the borehole monitoring case, or like the numerical experiment case as we shown in last year SEG, if we have adequate ray coverage, we can follow up with a loop C, which is to update the velocity and get a tomographic velocity image here. But in our field case study, we only have 7 geophones, and we have very sparse located events, so we don't have adequate ray coverage to perform a reasonable tomography. Therefore, we didn't include loop C in this workflow, but it's optional. Our data is from Pascal facility of the Incorporated Research Institutions for Seismology, known as IRIS. A major earthquake with magnitude 5.8 occurred on 23rd August 2011. And after that, 7 broadband and high-gain seismometer and accelerometers were rapidly deployed just to capture the seismic activities, because people doubt it could be related with oil and gas activities there, because it's supposed to be seismically quiet. And I have a video from the security camera inside of the National Monument in Washington, D.C., United States. And on the day the earthquakes occurs, the buildings start to shake. People are puzzled because nobody ever see earthquakes there. Until it shakes really crazy, people realize, oh, it's not good. They start to escape the building. So as I said, it's supposed to be a quiet. It may be related to the oil and gas activities here. Initially, people thought that way. And because of the rareness, the residents here were caught by surprise, and seismologist has no comprehensive model for it. That's why 7 seismometers were deployed there. It forms a T shape, and the cataloged earthquake within this for the entire year of 2011 is plotted here. All of them are very shallow. It's about 10 kilometers depth from the surface. And for testing purpose, we only processed 24 hours recordings on the day of August 29, because on that day there are 5 cataloged earthquake occurs in this region, and we use a homogeneous velocity, 6 kilometers and 3.5 kilometers for P and shear wave respectively. The red box marks the size of the search volume. It's 40 by 40 kilometers wide and 7 kilometers depth because we have no priority information about where the earthquake might occur on that day. And if we want to have a 2 seconds of scan window, the program decided to have a signal window about 16 seconds. And then to speed up the processing, we have to be selective on the data. We only perform the stacking when more than 4 stations have magnitude amplitude beyond this level, and at the same time, the short time analysis and long time analysis window ratio is beyond 2. So with that stacking criteria, signals like this will be processed. Those are weak signals in the data, but they're not recorded by the global network, um, the seismograph network. And events like this, dominated by background noise and maybe some local culture, will be ignored. And the amplitude is supposed to be a semblance enhanced and a polarization enhanced, as we described in the workflow. But because we use a simplified homogeneous velocity model, the polarization constraint from the model may be too off from the reality, and that may introduce significant bias. Therefore, we decided to let delta p equals to 1, and we only use semblance enhanced amplitude. And this amplitude is not a true amplitude; it is the short time long time window ratio over the characteristic function of p wave and s wave. The characteristic function of p wave following this paper is calculated using the vertical component, and the shear wave is calculated from the instantaneous eigenvector from the other two components. So the short time long time window over the characteristic function shows here, it shows it's well identified the arrival of p as well as the arrival of shear wave. So that is used as the input for the workflow. Using 48 cores on the CPU cluster, 24 hours of the recording was processed within 10 hours. And in total, we detect 176 events. And we group them in 3 categories. There are about 120 events in category 1 because they're called environmental noise and potential seismic signals because only one station has detected that signal. And they're actually more likely to be environmental noise. Events that are detected by more than one station, but not all stations, is called potential seismic signals, and there are 25 events in this group. And only signals that are recorded by all the stations are considered likely seismic signal, and there are 31 events, and those are the events subject to relocating of using our workflow. And we plot the histogram of the 3 groups as function of time. Blue is the environmental noise, red is the signal, and you can consider the yellow or the greenish yellow as the gray zone between signal and noise. And I converted the time from UTC time to the local time here. You can see 2 rises of seismic signal. One is occurred in early morning, August 29, and the other one is in the afternoon, August 29. So this rise is likely because of seismic events, and this rise has less located seismic events, and some of them maybe are affected by the local cultures there. So this information are very useful for us to distinguish if this earthquake is created by the oil and gas activity or it's just tectonic activities in those regions. It looks like more like tectonic activities in this region. So we plotted our located events here, top view and the side view, together with the cataloged earthquake. And there's some offset, and that's because of the grid interval we use, and probably also the model we used here. And looking from the top, it forms an east and north direction. If we check literature, there's a report saying there's a northeast strike system in this region. So that's probably consistent with that. And we can also compare with the catalog data within a whole year. 24 hours of data processing already give us very good information about the seismic activities, and it can locate more events, much more sensitive than the global seismic network. So we have developed a workflow start from events detection or events harvesting to locating and to nonlinear inversion. If we have adequate recoverage, we can follow up with velocity updating. We have validated this technique on numerical experiment in a conference paper last year, and in this talk we have demonstrated its performance on a field recorded surface seismic data, and pseudo real-time feedback is possible using coarse grid because 24 hours data is finished in 10 hours, means 1 hour's data can be processed in 25 minutes, and that's pseudo real-time feedback. The coarse grid effect will be reduced, and the spatial resolution can be increased by a subsequent hypocenter parameter inversion, and the classification of the triggered events into subgroups will give us a better idea of local seismic activities. It can give us better ideas, if it's oil gas activity related or if it's tectonic activities related. The other applications in this short discussion can be reservoir monitoring on the surface or near surface or the borehole. It can be applied straightforward to hydraulic fracturing monitoring. It can be induced earthquake monitoring, to distinguish if it's oil gas activities or it's the tectonic activities. And if you have some data sets sit in the corner of the office, this workflow can help you reprocess that events with the interface with a processor, so you can actually detect more and events and more reliable events. So finally, I just want to remind you this workflow or process unit can be applied to borehole monitoring, near surface monitoring, and the combination of both. Thank you very much.